Hey guys, Dr. Betts coming with another fantastic chemistry video, and today we're going to learn all about carbohydrates. Ooh, scary word you're not supposed to say in polite conversation. Carbohydrates. Oh, they're awesome, guys. I mean, I know we eat them, we get fat. Everyone doesn't, no one likes that, but they're delicious. Come on, this is space family. Potatoes and rice are good. Why? Because we're designed to eat them. We're designed to use them for fuel. We're designed to be carbohydrate consuming machines, and they're yummy. They're good fried, especially as French fries. Let's face it. We're going to learn all about carbohydrates and what they are and where you find them. Okay, we're going to learn about amylose, amylopectin, cellulose, glycogen. We're going to learn all about them. We're going to learn about alpha glycosidic bonds, beta glycosidic bonds. We're going to do modeling. We're going to do experiments. It's going to be epic. So let's stop talking about it. Let's get after it. Let's get it done. And now I'm showing you the dry part of the lab where you just have to look at some models and essentially draw what you see. Because you can't be in the lab to see the models, I'm going to have to basically present them as still photographs, unfortunately, and then kind of draw them for you, trying to point out things along the way. It's not the ideal situation, obviously, because this is where we're at with this virus, but this is what we're going to do, okay? So now just please bear with me, work with me, and we'll get it done. Now, as you can see here, we're looking at a molecule of glucose here and another molecule of glucose here. So I'm up here, guys, in case you're wondering where I am. So we're going to have two glucose molecules come together. And what I want you to do is I want you to draw these glucose molecules in your book. Now, I'm going to draw them right now. You just draw what I'm drawing, okay? Now, let's take a look here. Here we have an oxygen back here, which is bonded to a carbon, which is bonded to another carbon, which is bonded to a carbon, to another carbon, and then there's a carbon back here. I know it's difficult to see from the photograph, or somewhat difficult, but there's 1, 2, 3, 4, 5, 6 atoms in a cyclical or cyclical conformation. So let's just draw that. Carbon to oxygen to carbon to carbon to carbon to carbon, and then they're bonded together. So there's my 6 atoms in a circle. 1, 2, 3, 4, 5, 6. Okay. So there's my 6 atoms in a circle. 1, 2, 3, 4, 5, 6. This carbon here has a carbon OH coming off the back. I know it's hard to see, but there's a CH2OH coming off here. This oxygen here is bonded to that carbon. This is your anomeric carbon, so it's this carbon here. Now, I'm not showing you whether these OHs are up or down. I'm just drawing them in. I'm just drawing them in because it makes our life a little bit easier. There's a hydrogen here, and there's an OH there, and a hydrogen here, and an OH there, and a hydrogen there, and an OH here, and a hydrogen there. And essentially, this molecule here is exactly the same. So let's just draw that. All right, and then there's a CH2OH off here. All right, so essentially these two things are exactly the same. So I'm just drawing them pretty much exactly the same. Again, I'm not really worried about the up or downs of these OHs in this class. It's not really that important for you guys in this class. Now, in the disaccharide, I'm going to be a little bit more concerned with the up or down of the glycosidic bond. So now we're going to draw D-maltose. Here's a structure of D-maltose. Here's my 6-membered ring. 1, 2, 3, 4, 5, 6. Here's the glycosidic bond right here. And here's the other 6-membered ring. 1, 2, 3, 4, 5, 6. Okay? So again, 1, 2, 3, 4, 5, 6 atoms in a ring. Glycosidic bond, there's the anomeric carbon. 1, 2, 3, 4, 5, 6. And there it is. There's the glycosidic bond. I'm kind of using my laser pointer here to really drive home what I want you to look at. Right there. This glycosidic bond. So we'll draw that. It's going to look a little bit complicated, but it's not that bad, really. Now this O is going down. Notice I drew it in the downward direction. There we go. And again, there's other things on these carbons. Now, these hydrogens I just drew have to be up, okay? Because this oxygen is down. These two hydrogens must be up because this is an alpha glycosidic bond. Okay? It's an alpha, oops, you can't see that word bond, can you? Here we go. Alpha glycosidic bond. So let me just finish drawing in the accompanying OHs and Hs. If I'm going too fast, you just pause the video so you can draw them in yourself. There we go. All right, so there's that one. Now again, beauty of YouTube, you can pause the video right now and watch this part again if you didn't get it. But I think I did a pretty good job. Let me just put it, I messed the hydrogen up here, guys. Sorry about that. All right, next. Now we're getting what we have right here. This is a glucose molecule. What we have right here, this is another glucose molecule. And this right here is a third glucose molecule. Okay? It's impossible to see on this picture, really. It's not impossible, but it's very difficult. I know what I'm looking for, so I can see it. I want to focus your attention here. That's the glycosidic bond attaching these two sugars. Notice how it's going down. That's an alpha glycosidic bond. Here's another glycosidic bond over here. It's going down. So this is the portion of the polymer amylose. Amylose is a polymer of glucose, but in the polymer, all the glycosidic bonds are alpha. That's amylose. So I'm going to draw this, but I'm going to draw it as a skeletal formula just because it's so much easier. And I think you'll be appreciative of it because it's so much neater. The maltose I kind of drew as a, I kind of drew the maltose as a expanded formula, just kind of drive home the point. But with these big polymers, I like to draw them as skeletal formulas simply because it makes your life a whole lot easier. Now at this point, the polymer will continue, and the polymer will continue. The polymer will just keep going from left to right. And of course, we have to draw on our accompanying stuff. And it doesn't really matter what these H's and OH's are, just make sure they're in. Oops. I'm not going to judge you guys on it, and I'm not even being all that careful with it right now because of the urge and the necessity to get this done, because we all have lots of things we have to accomplish before the end of the week. But you get the idea. This is a polymer of glucose. This is amylose. How do I know? First of all, it's not branching. Second of all the glycosidic bonds are alpha. That's how I know. Here is cellulose. Now, again, it's difficult to see from this photograph. I'm going to walk you through it. Here's a glucose molecule here. Here's another glucose molecule here. And here's another glucose molecule here. So this is a portion of cellulose. And again, I'm just going to point out the glycosidic bond. Notice how it is going in an upward direction. So the glycosidic bond is actually beta. Cellulose is a polymer of glucose in which all the not all, but a lot of the glycosidic bonds are beta. Sometimes there's a few alpha mixed in, but some of them are beta for sure. So let me just draw that as a skeletal formula again, just because it's neater. But remember, cellulose is indeed glucose. It's made of glucose. It's just that the glycosidic bonds, some of them at least, are beta. I'm just, in this polymer, we just kind of drew them all beta just to drive home the point. All right, and let's just draw in some of the accompanying things. Notice I drew all the glycosidic bonds in the upward direction to clearly indicate this bad boy is beta. And again, where you put all the accompanying stuff is not really that important in this class. It is important, absolutely, in reality, but in this class, I don't get too crazy about it because it's challenging to know and to remember, and it really doesn't mean anything unless you're taking some organic chemistry. We could tell you, but it wouldn't mean much to you. There you go. So that's what it looks like. Now, I get it, guys. This is crazy. These models are set up in the lab. Normally, students would have the chance to pick them up, look at them, examine them closely, ask questions about them. But unfortunately, because of the shutdown, this is what I decided to do to kind of help you all. But don't fret. If you have any questions, I'll be around for office hours during the scheduled times next week on Skype. So go ahead and give me a Skype call or hit me up on Skype, whatever you need to do. But let's work together. Let's get through this situation, and I think we're going to come out stronger on the other end. All right, guys. Thanks for your attention. With that, I want to wish you good luck and good chemistry. Now we're going to do the Benedict's test for reducing sugars of carbohydrates. Here I have some test tubes. One test tube has glucose, one has sucrose. And I'm going to add a little bit of the Benedict's solution to each one. There you go. Let me see if I can get that to the camera for you. There you go. Benedict's reagent to each one. So let me get my goggles on just in case. How much Benedict's solution do we need? About 1 milliliter of Benedict's solution. All right. So here we go. There we go. It's a little tight. And we get 1 mil. That's about it. There's 1 mil. So I'll put 1 mil in with the glucose. There we go. Put it in the heat. Now I'm going to warm this bath. Is warming up now. I want it to kind of get close to boiling, if not boiling. We may see the result before boil, though. Let's keep that in mind. All right. There. Now we're just going to let them sit in the solution. This one here is glucose. This one here is sucrose. All right. So now we just sit and we wait for something to happen. And I think if you look, you can already see something is definitely happening with the glucose. It's starting to change color. Let's give it a little more time, a little more energy in the heater, see what happens. But you can already see definitely something is occurring with the glucose solution, not the sucrose solution though, so that's interesting. We're going to let that go for a few more minutes. Okay guys, I think that we can call it right now. You can see the glucose solution has definitely changed to a kind of an orangish red solid looking material. So it's definitely reacted with the Benedict's reagent. The sucrose on the other hand is still staying blue. Benedict's reagent is that color, so it's not reacting with the Benedict's reagent. So there's some information for us. Write that down in your book. And let's get on to the next step.
Hey guys, let's continue on with our experiments with carbohydrates. Now we're going to do the hydrolysis of a polysaccharide. I've got 2 test tubes filled with starch. Let me grab them for you. There you go. As you can see, starch is basically more or less a cloudy type suspension. This is kind of how they look. So as you can see, that's what they look like. So now we're going to add acid to one, water to another, and we're going to do what's called a hydrolysis reaction, or we're going to see what happens when we do a hydrolysis reaction. So let's do that. So here is my 3 molar hydrochloric acid. I'm going to add that to the one labeled acid. I think it says 3 drops. So I'm going to do 3 drops. Actually, it's 5 drops. There we go. So there's the one labeled acid. Give that a little shake. And now I'm going to add some water to the one labeled water. Just going to use a squeeze bottle for that. 5 drops, best I can. There we go. That's about 5 drops. A little more than that, but that's okay. And now I'm going to put them into the, as you can see, they haven't changed much. They really didn't change at all. I'm going to put them into the hot water. And I'm going to let them sit there for about 5 minutes, 5 to 10 minutes. 10 minutes, it says. So there you go. Let's let them sit there for about 10 minutes. Let's crank that up a little more, get the water to boil. All right, guys. See you in 10. All right, guys. It's been about 10 minutes. So let's take our samples out and let them cool down for a few minutes. Okay, guys. Now that our samples have cooled down a little bit, here's what they look like. After heating them, they got a little clearer. There you go. They're more or less comfortable to touch. So now I'm going to do a pH test. I'm going to take a piece of pH paper, which tells you the pH by color. And I want the pH of this acid solution to be above 7. Or to be 7 actually would be ideal, but if it's a little bit above 7, that'll be okay. So let's dip it into here. Now this most definitely, just let me get on frame here. This most definitely should be acidic, right? Because, we added acid to it, right? And there, as you can see, it's red. Red is right around pH 2, just so you know. So this is acidic. So now I'm going to add some sodium hydroxide to counter that, to make the pH come back to about 7. I'm going to add a couple drops. It says in the book to add a ml. I'm just going to add a couple drops. See what happens. 1, 2, 3, 4, 5. How about 5 drops? Probably going to regret not just adding a ml, right? Always follow the instructions, as they say. Sorry, this video seems like it's getting a little dark. Kind of doing these things last minute here, so bear with the production quality. He says like he can make it really good anyway, right? So let's try this again. Here we go. Still acidic, so let's add some more. I just added a boatload, about a half mil. I added about a half mil, to be honest with you. I'm going to stir it up a little bit, get it nice and homogeneous. And let's check. There you go. See, now it's blue. That's basic now. I've went a little higher than pH 7, but that's okay. That's okay. We'll be okay. Now, at this point, we want to get a sample of each one. So now I'm going to take a spot plate. I'm doing the iodine starch test on page 114. I'm going to take some of the one labeled acid. So let's put an A over here, and then we'll put a W here for the acid and base. Let me get my other camera adjusted here, guys, and I'll show you what I'm doing. Okay, class, now that we've taken our samples of starch and treated it with acid and treated it with water and then heated it for 5 or 10 minutes, we're going to try to see what the result of our experiment is. In well number 1, this well right here, we're going to put our starch and water solution. So let's just put 5 drops in there. 1, 2, 3, 4, 5. This was the starch treated with water and heat. And we're going to treat it with an iodine solution. Now this iodine solution will turn black in the presence of starch. Here's what the solution looks like on its own. It's kind of a yellow color. Okay? So that's the solution on its own. Let's take a little drop and put it into the iodine solution. Now, as you can see, it instantly turned black. Instantly turned black. And that is very positive for the presence of starch. So starch plus water plus heat equals no reaction, essentially. Basically, you get starch back. Now, I'm going to take 5 drops of the starch solution, treat it with acid. 1, 2, 3, 4, 5. This is the starch solution, treat it with acid. Let's go ahead and put a drop in there, see what happens. There we go. And as you can see, it did not turn the same color. It stayed the yellow color of the iodine solution. So that tells me that there's no starch present in that sample. So think about it for a minute and try to determine what must have happened when we added the starch to the water and heat, starch to acid and heat. What must have occurred in that flask? All right, guys, I'll let you think about that. Write it up in your data sheet, submit it to your instructor, and presence of Benedict solution. So now we're going to test our starch digestion, the acid in starch, to see if there's glucose there. So let's do that experiment right now. I'm going to add a milliliter of Benedict's reagent to each one. So here's my acid. Here's my test tube that's labeled acid. I'm going to add about a milliliter of Benedict's reagent to it. Let me get rid of this bottle here. Get that out of the way too. About a mil. It doesn't have to be too accurate, but about a mil. All right, so put a milliliter in here. And put that back in the water. The water is nice and hot, so this shouldn't take very long. I'll make sure my other camera's picking that up. All right, very good. That's about a mil. Put it into this is the water one here. Okay, guys, that's the water. Water and starch together that we heated up for 10 minutes to near boiling. All right, let's put that in there. All right. Here we go. Let's just sit and wait now to see what happens. The glucose is definitely turning brick orange or brick reddish orange. That's a positive test for glucose, so that's really kind of cool. The acid solution in starch, after heating it for about 10 minutes in near boiling water, the starch digests it into glucose molecules. And then the glucose molecules we confirmed using a Benedict's test. The Benedict's test for glucose told me that this is most definitely a digested starch with glucose present. Isn't that kind of cool, guys? All right, guys.